Hello and welcome to another video regarding operational amplifiers. We'll be talking about another type of operational amplifier, which is differential operational amplifier. So as the name implies, this is used to find the difference between two input signals. So if I have signal 1, which is a voltage, so V1, or let's say V1 and V2, and I want to find the difference between these two voltage signals, we can use a differential operational amplifier to do the difference. And we are going to see how this really works, how we are able to use this to find the difference between two signals. So let's say signal 1 and then signal 2. Okay. Now, as you can look at, you can see on the screen, we have an operational amplifier and we've added some resistors to the operational amplifiers. And this kind of operational amplifier kind of look familiar. If you look quite well, you can see that if we're to block out the side, you can see that part is just distant. Would they resemble an inverting operational amplifier, right? So, and similarly, if we're to block, for example, if we're to maintain this part, right? Here we maintain here, but then we block this part again. And then here we look at the fact that we have an input signal to this, and when this is grounded, you can see that also resemble a non-inverting operational amplifier. So when it comes to a differential operational amplifier, it's a combination of both inverting and non-inverting operational amplifier that is used to design and then make a differential operational amplifier that we have. Now, how do we determine the output voltage? All right, so we want to again find the relation between the output voltage and then the input voltage sources that we have. We have V1 and V2 as our input voltage sources. We want to find the difference between these two input voltage sources. And to do this, we are going to be using superposition theorem, right? Or when it comes to superposition theorem, it is the algebraic sum of voltages across an element in a circuit diagram due to each of the voltage sources in the circuit diagram acting alone. And we are going to be using this principle to find the output voltage. So when it comes to output voltage, which is our interest, you can see that we can use superposition by saying that, okay, that means output voltage 1 plus output voltage 2, the two sum together, every sum should give you the output voltage. Now, in doing this, we have to try and then get output voltage 1, and to get output voltage 1, we look at the fact that that very signal, mean the voltage source there is being active, while that of what V2 is inactive. So meaning we turn off what V2. So if V1 is active and we're to turn off V2, to turn off a voltage source, what we do is that we short circuit the voltage. I mean, you just connect a wire to this, and then we get something like this. So as we can see, this place is now like grounded, right? So this V2 is being short circuited. And since there's no voltage supply to R2 and R3, right? So meaning, in a way, this is just really connected to the non-inverting input, and this just become an inverting operational amplifier. So since we don't have any voltage supply here, we can just make this one even this way. Just connect this, because the voltage across all of that will be 0. So we get this become just an inverting operational amplifier. And when it comes to an inverting operational, we know how to get the output voltage, which is going to be minus RF over R1 times V in. V in is a voltage source, right? When it comes to the input voltage, so when it comes to inverting operational amplifier, and here that is going to be V1. So V in here is just the same as V1 here. Then we get this formula. Okay. So that is how we get the first output due to V1 acting alone. Then we have to get now the second output due to V2 acting alone. So this time V2 is acting alone, meaning V1 is going to be turned off, and it's being turned on by connecting a wire. That means you also keep the this in there, the voltage there, V1. So we have something of this nature. So as you can see, this here resembles a non-inverting operational amplifier. And we know the formula for non-inverting operational amplifier, which is 1 plus RF over R1 times V in. The V in here, as you can see, that is just what the voltage input into the non-inverting terminal. So that will be what we labeled here as a node. So I'll label that as node B. So we can refer to this node, which is going to be the input into the non-inverting output input terminal here, to me, VB, right? So we have voltage at point B. And that's why we end up. So V here just one VB. And to get VB, as you can see, again, when it comes to an operational amplifier, the current input into the operational amplifier is 0. So as you can see, if that current which is here, let's say II is 0, that means you can see that if there's a current flow from V2, that means just passing through this, right? R2 and R3. So they become in series. So the voltage at what B would just be the voltage across R3. All right. And remember, I is 0. So yeah, R2 and R3 be in series. And to get the voltage across R3, which is what the voltage at node B, that will just be equals to 1. The resistance, which is R3, over the sum of the resistors in series, and that is R2 and R3 times the voltage supply here, which is V2. So we get VB2 equals to this. Then we come and replace VB, then we get this formula. From there, we can find and simplify this formula by saying that, okay, in order to really simplify this, what we can do is that we can make sure that R1 plus R is just the same as R2 plus R, so that the numerator and denominator they will cancel. And to achieve that similarity, what we can do is, I have to make sure that R1 is equal to R2, RF is equal to R3, as we can see here. So if we put R1 to be equal to R2 and RF being equal to R3, then this will cancel this. So R3 just RF. So we just have this. And then we end up getting the final formula to be equals to the output voltage will then equals what? V. RF minus RF plus V2 minus V1. And this is how we are able to get the output voltage. And remember here, again, we are doing algebraic sum. We've gotten V2, V1 due to the output voltage due to all V1 being active, as well as that for V2 being active. After that, we do algebraic sum, we simplify. That will give us the final formula to be equals to RF over R1 into brackets V2 minus V1 as the output voltage for a differential operational amplifier. See you in the next video. Bye-bye.